Hello everyone, welcome to this session about quantum and quantum-inspired annealing. What we're going to do in the next half hour or so is to just have a look at what annealing is, why you might be interested in it, what is out there, what the state of play is of this technology, and what it's useful for. What we're going to do is just a brief introduction of why you might be interested, what it is, the annealers that are out there, the state of play of the technology, and then the meat will be to just talk you through the benchmarking exercise that we went through at my company, Objectivity, what we tested, how we tested, what we found, and finally bring it into land with conclusions. This is a very practical session in the sense that we're interested in technology as it is today, not as it will be 10 years from now. We're not a research institution. We're here to solve our customers' business problems. So the focus will be very, very practical about what use is this quantum and quantum-inspired technology today. A little bit about me. My name is Peter den Haan. The funny accent is Dutch. I'm quantum computing specialist at Objectivity, which is part of Accenture. I started life as a physicist. I've got a PhD in quantum physics on aspects of quantum electrodynamics and anti-de Sitter space. I've also got 12 years experience as a software developer, mainly using Java, Clojure, and JavaScript. So that's enough about me. Let's start with a short introduction. We're all familiar with quantum computing, right? The reason why quantum computers are potentially so much faster and scale so much better than anything else out there is entanglement. It's the sheer size of Hilbert space. And here is I probably don't, anyone who attends this conference, I don't need to tell you what quantum computing is, but there's a little illustration for you. It's like a classical computer solves a problem, a maze, just one step at a time, but with your entangled qubits, you can explore an entire problem space and ask a question in one go and solve certain classes of problems much faster. In the business world out there, most industries are by and large convinced that quantum computing is going to be significant. Even significant in the short term. By 2025, about half of companies believe that quantum computing will start to impact really practically. Virtually everybody thinks that in the long term there will be serious disruption, as in improvements that can get you a competitive advantage or can get your competitors a competitive advantage across all industries. And actually a lot of companies are already starting to pay attention and are expecting relatively short-term impact, relatively short-term systems out there that will help them do their business better based on quantum computing. In reality, though, you probably know the predictions of when quantum computing will become practically useful just vary widely. Some people say, the first application is already useful now. You can use this stuff actually even in production. You hear other voices who say, well, no, quantum computing is going to be up till 20 years from now, it will become useful, maybe more. And what to think of this? Well, it really depends. It really depends on what you're looking at. If you're looking at, breaking cryptographic encryption using Shor's algorithm, then yeah, that will be a little while from now, because you need quantum computers with a significant capacity. You will have to address the noise problem, error correction, circuit depth, all of that, and we're a long way away from that. But, the quantum computing life doesn't start and end with Shor's algorithm. So the answer to the question, when does quantum computing become useful, depends on the use case, the problem you're trying to solve, in other words, the technology you're using. So when you think about quantum computers, by and large, people think about circuit-based quantum computers, or alternatively gate-based quantum computers, means the same thing. And well, we got the early ones were about 100 qubits. They're noisy, circuit depth is limited, decoherence is a problem, and so on. So actually, I think that it will emerge into some practical usefulness, early use cases that might be sort of commercially useful sooner than many people think. But we're not there yet. Then there are annealer-based quantum computers, which work in a completely different way, which are focused on optimization. So they're kind of single-purpose circuits. And actually they're in a much greater state of maturity, in part because it's simpler, it's easier to scale. And actually with annealing, noise isn't that much of a problem. We'll come back to annealing in a moment. And then finally, of course, there is actually the ideas, the foam of ideas that quantum computing has generated has actually impacted the classical world as well. And there's a world out there of quantum-inspired algorithms. And we'll come back to that as well. So what will the quantum computing world look like? I will go over this briefly because I assume that most of you will know what to expect. For selected use cases, we can see the first commercial use of quantum computing. As I said, annealing is actually already useful. Things like atomic clock, quantum key distribution, the networks are already up and running in many places in the world. Quantum machine learning, as you can see on a little diagram, that is probably sort of the next wave of early applications of quantum computing, but is in the process of emerging. Early simulation, again, that's sort of the medium term. It will be there, start to get there in a few years. The big promises of quantum computing, those exponential speed ups, they're a bit further into the future. But that is, we need more sophisticated hardware for that. We need error correction and all of that. But the early use cases are already here. And the early use cases, we think the earliest use cases that are already here now are based on annealers. So let's specifically take a look at annealers. And I don't assume that everyone is completely familiar with annealers. So let's start by having a look at what they are and what they do. Annealers are based on the idea of the annealing process in metallurgy. Sort of when you heat a metal and the atoms of that metal, they're sort of in a fairly reasonably chaotic state, and as it cools down, it settles into a structure and at a sort of an energy minimum. And that is the basic idea of an annealer. You start with a superposition of states with the Hamiltonians, it is well defined, and then you start slowly changing the Hamiltonian, and slowly changing, as it were, the temperature of your system to a Hamiltonian that represents the problem the optimization problem you're trying to solve. And there is something called the quantum adiabatic theorem that says that if you make that change slowly enough, and you start in a minimum, you start in an optimum, then you will also finish in an optimum. So that means that at the end, when the Hamiltonian represents a problem you're trying to solve, the state of your system, the state of your quantum annealer, will represent the minimum of that Hamiltonian and therefore the optimum of the problem you're trying to solve, which is fantastic. Now you might ask, slowly enough. What does slowly enough mean? Well, of course, there's the rub. you can sort of formulate heuristics of what is slowly enough. But you can't do it too slowly, because in the end you want your answer at some point. So there's a little bit of an art to that, but that is the basic idea. You can see this in the diagram. You start in a superposition state, you start to modify the Hamiltonian of your system to represent your problem, and hopefully at the very end you find the system into the minimum of the Hamiltonian, and therefore the optimum of the problem, the optimum that you're looking for. It's probabilistic, so you're probably going to do this 10 times, 100 times, 1,000 times, and then look at the distribution of your solutions to pick out the one that represents the optimum or something very close to it. And generally you can pretty much guarantee, although it's all heuristic, you can pretty much guarantee that you will end up with something that is either the optimum or something pretty close to the optimum if you do your job right. And there's a little bit of an art, to be fair, to doing the job right. There's of course science to back it up, but there's also an art to it. One of the sort of characteristics of annealers, apart from that they're sort of single purpose optimization circuits, tunneling plays an important effect in quantum annealer specifically, because tunneling allows the system to transition from an energy state that is a local minimum but not your absolute minimum, in other words not your optimum. Tunneling allows your system to transition from there to a better minimum, and hopefully, ideally, the absolute minimum, in a way that is classically impossible. And it has been demonstrated in an article called Computational Multi-Qubit Tunneling in Programmable Quantum Annealers in 2016 by Bosio et al. Has been demonstrated that tunneling actually works in that way and helps the quantum annealers perform the way they do. Entanglement actually also plays a role. There's an article I would recommend as re-examination of the evidence for entanglement in quantum annealer by Albash et al. And in 2015 that was published in PhysRev A. Bosio was published in Nature. And the final thing to note is that you will be surprised by the number of problems that can be formulated as optimization problems to run on a quantum annealer. All of CARB's 21 MP complete problems can be run on a quantum annealer. That's been as a famous paper by Andrew Lucas called Ising Formulations of Many NP Problems. And it was published in Frontiers of Physics 12, and graph covering problems, traveling salesman problem, bin packing problem, partitioning problems, the number of problems that you can formulate as an optimization problem, in fact as a binary optimization problem with quadratic interactions, which is what annealers specialize in. Binary because they're qubits, and quadratic interactions are what we can model using an annealer. The number of problems that can be formulated in that way is enormous. You would be surprised. That's really a paper I would suggest you read if you're at all interested. And in terms of where the technology is at, D-Wave, which sort of the premier quantum annealer company, has hardware running available on the cloud. If you want it, you can get access to it for free, and it's got 5,614 qubits, and they're looking to expand that to 7,000. So that's where the quantum annealer technology is at. D-Wave is the prominent player in the quantum space. There's a whole host of people who've been inspired by it in annealing lark and are running quantum-inspired annealers. And they generally use FPGAs, so programmable gate arrays, or they use sort of graphics cards, a whole host of graphics cards, or classical computing resources, your CPUs. Toshiba and Fujitsu have annealers. You can find one qubit and Microsoft Quantum inspired annealing on Azure. There are startups, many startups working on this space. Quantagonia we have tested. We're currently talking to a company called LightSolver. This is not an exhaustive list, but there's a lot of people working in that space, because actually businesses are out there are riddled with optimization problems that are perfect for annealers, and annealers are actually already emerging into commercial usefulness and can really demonstrate value if you pick the right use case. And that is only sort of the set of use cases where you can get value is only going to expand and expand rapidly over the next few years. So there's quite a few players in this space. And we try to benchmark as many of them as we could put our hands on. Because, as I said, we're a company. We're here to solve our customers' business problems. So we're interested in near-term use of quantum and quantum-inspired computing in a production context. Of course, we also work with circuit-based quantum computers, because it is our job to spot where and when they will be useful for our customers. But at the moment, an awful lot of our work is done with annealers, so we want to know what tools are available in the market, how well do they perform, across a range of different problem types, what are the strengths and weaknesses. So we tested a fair number of them against a number of different problems, and we tested them with fixed timeouts so as to create a level playing field. And the problems that we used, you can see them here on the slide on the right hand side. The problems that we selected is the Sherrington-Kirkpatrick model, which is a spin glass. It's perhaps slightly artificial, but a sort of fully connected, fully interacting matrix. The second model is in some ways quite similar. This one is pulled from an early application of quantum computing in the AI space, which is feature selection. So imagine you want to build a recommender system based on artificial intelligence, and you want to recommend stuff based on the property of the items you're trying to sell. Now you have sort of a data warehouse or a data lake with all the properties of your items. If you try and train your machine learning model using all the properties, it probably isn't going to work all that well. But if you pick the right optimal subset of properties of your items, the properties that are most significant, so that you sort of recommend the best possible article to your customer, then your AI will work much better. Well, picking those features that you use as input for your AI, that's an optimization problem, which set of features to pick. And that is actually one of the places where annealers work really well. So that's a feature selection model. Again, highly dense interactions, sort of many interactions between different elements, between the different variables of your model. One constraint, which is the number of features that you want to end up with. Pick the optimal set of features. The third problem that we ran, traveling salesman problem, most or all of us are familiar with it. You need to visit, say, 10 cities. You know the geographical locations, the distance between cities. You don't want to visit cities twice. What's your best route? Actually, very simple problem to state, computationally hard problem to solve. Impossible to, without short-circuiting, without sort of shortcuts, heuristic shortcuts, it's impossible to solve classically within an acceptable time frame as soon as the number of cities grows. Annealing works pretty well there. So traveling salesman problem. Bin packing problem. I've got a number of bins of given size or given weight. I've got items of a given size and weight that I want to put into the bins. What's my optimal packing? That's the bin packing problem. Again, it's an optimization problem. And the final problem, just to assess the performance of the annealer on integer variables. What you need to do with integer variables, you end up coding them down to binary. which creates a sort of pretty messy Hamiltonian when you need to do that. So to assess how well an annealer behaves, because in practice, many optimization problems actually involve integer variables, not just binary variables. We formulated a simple integer linear programming problem, which is, I've got a pile of pizza ingredients. I've got recipes of pizzas I can make. I know how much the ingredients cost. I know how much I can sell the pizzas for. Which pizzas do I need to make in which quantities to maximize my returns? Again, very simple problem to state. Actually, this is not a particularly hard problem to solve classically, as I just stated. And you wouldn't use an annealer normally to do it, but it allows us to assess how well does this annealer handle integer variables when you have to code them down to encode them as binary variables and stick them in the Hamiltonian in that way. So let's have a look at the results. So the first one, Sharon Kirkpatrick's spin glass, which is sort of a physical system. Highly dense interactions between sort of all the different variables, all the different spins in your spin glass. Perfect use case for an annealer. And you can see the results here in front of you. Now let's just go in a little bit more detail slowly for this particular case and familiarize ourselves with what we tested. So the blue line, the light blue line is D-Wave. It's the D-Wave cloud service. So that uses the D-Wave quantum processor supplemented by a large amount of classical computing resources. And D-Wave won't tell you how exactly they mix up the two, but it works exceptionally well. In terms of compute time, most of the compute time is done by sort of classical computers, and the time spent on the actual QPU is measured in milliseconds, whereas sort of the total execution time, depending on the size of the problem, is measured in minutes, seconds or minutes. And sort of on the x-axis, we increase the size of the problem. On the y-axis, you find a percentage, which is basically the quality of the solution as measured by the energy of the Hamiltonian compared to the best possible solution that we've got. And you can see that the D-Wave Cloud Service does an absolute great job on this particular problem and is basically pegged at 100%. Within a given time, comes up with the best solution of all. The next one is the Microsoft Quantum Inspired Optimizer, which you can access very cheaply or even for free on the Azure Cloud Service, which does, they're all going up to a scale to 10,000 variables, 10,000 binary variables. Does pretty well, starts to drop off a little bit at 3,000, 10,000 variables, but does a pretty good job. A startup, Quantagonia, which at the time of testing was in a really early stage, so with a sort of maximum number of variables of 8,000. So, you know, this is clearly sort of an early effort. Did pretty well, but started to drop off really at size 1,000, and beyond 3,000 you start to hit the limit of the hardware. 1 qubit, which is also available on Azure, didn't scale terribly well, performed similar to Quantagonia, but actually didn't really scale fantastically well. Toshiba is another pure quantum inspired annealer. MSQAO, Quantagonia, 1 qubit, Toshiba, they're all quantum inspired rather than quantum as such. Toshiba performed very similarly to the D-Wave hybrid offering. Found the optimum solution to the spin glass problem, right up to 10,000, which is where the hardware starts to reach its limits. Then we also tested just a D-Wave QPU, rather than sort of cloud service with the sort of classical resources isolating you from the QPU. And the QPU did pretty well, but you can get it to about 100 variables. Now you might wonder, why can you only get it to 100 variables when the QPU has more than 5,000 qubits? And the reason for that is connectivity, because quantum-inspired annealers generally have perfect connectivity. You can have interactions between any two qubits, but a hardware implementation is generally more limited, and the sort of the connections are only between specific qubits. And D-Wave over the years has been working with a number of different topologies. But what you need to do when you have a problem is to find an embedding of your specific problem on the physical structure of the quantum processor. And in order to sort of deal with the limits of connectivity, you quite often need to use multiple physical qubits on a quantum processor to represent one logical qubit. And you do that by basically creating a very, very strong interaction between them, so they always have the same value. So actually you can lose, depending on the particular topology of your problem, you can lose an awful lot of qubits that way. And that is what is happening here, because the spin glass is a fully dense interaction matrix. It's a fully connected problem. So it's a nightmare to embed on the QPU. And that is why the D-Wave QPU, we couldn't get beyond 100 qubits because of the nature of this particular problem. And then just to benchmark these quantum and quantum-inspired solution against a known quantity, we also benchmark Gurobi as a sort of best-in-class classical optimizer. And Gurobi is really, really good. But this kind of problem, a completely dense interaction matrix, you don't have any clever mathematical algorithms that you can use to sort of shortcut your way to the answer, is a perfect nightmare for classical optimizer like Gurobi. So you can actually see that within the given time frame, Gurobi absolutely does a good job, but the quality of the solution starts to drop off a little bit at the larger sizes of especially 3,000, 10,000 variables. This is really the kind of territory where an annealer really works very well. The next one up, feature selection. As I said, it's actually a really practical use case, an early use case for annealers in the AI space, selecting the features to input in a machine learning system. In many ways, it's similar to SK, as in it is the interactions are highly dense. There are a bit more variety in the interactions, and there is a single constraint, and that constraint is the number of features that you want to use. And you can see very similar behaviors. The D-Wave cloud service, which combines the QPU with classical computing resources, performs really well across the board. MSQIO and Quantagonia start to drop off at the larger sizes of 300,000, 3,000 features. 1 qubit we weren't able to run. Toshiba performs very well, and scales all the way up to 10,000, but starts to drop off a little bit in quality at the larger sizes of 3,000, 10,000. You can up that quality by simply giving it more time, but we're working with a level playing field here. Gurobi actually does better. Perhaps because the constraint gives the whole problem a little bit more structure, but also sort of drops off at the largest size of 10,000 that we tested. Traveling salesman. So you want to visit a number of cities, you know the distance between each city, what is your optimal route to go from the starting city to the city where you want to finish. Again, the D-Wave cloud service up to a size of 300, and actually the Cubo, sort of the optimization problem for a 300 city traveling salesman problem, the size optimization problem scales quadratically. So you're talking about 90,000 variables here. This is not a small problem. D-Wave performs well across the board. The Microsoft quantum-inspired optimization starts to struggle beyond 10 cities. Quantagonia, similar story. Toshiba performs a bit better, but starts to drop off seriously beyond 100 cities, and then beyond that you start to run into the limitations of the hardware, of the number of variables it can handle. The QPU, the D-Wave QPU, has a total nightmare with this particular problem. We managed to run it for size 3, and beyond that you run into embedding problems. Ruby, again, does reasonably well, but struggles at larger sizes, 30 cities or larger, to get acceptable solutions. At 100, 300, you need to give it more time. The technology really needs more time. Then bin packing. Sort of bin packing is where you have items, a number of items with given weight. You have as many bins as you need with a given maximum weight. How do you pack the items in the bins optimally so you use a minimal number of bins? Actually, annealers, when you naively translate this problem into a binary optimization problem suitable for an annealer, you get a Hamiltonian landscape that is really, really rough for annealers. And you can see here that almost all annealers really start to struggle beyond 10 items, with the exception of D-Wave, which of course supplements their annealer with classical computing resources. And so it performs better, but it starts to struggle at 100 items as well. So here you see an example of a problem that annealers cannot solve very, very easily. However, it is actually possible to reformulate the bin packing problem as using sort of a two-step algorithm by first finding packings for just one bin and treating them as a set of candidate solutions, and then in step 2, where you're trying to solve the entire problem, the problem becomes a graph covering problem, which is a lot easier for annealers to solve. We're actually working on that. We're busy benchmarking that, unfortunately not in time for this presentation, but it will be interesting to see how the technology is scaled then. But that's just a hint that annealers are not necessarily sort of your natural choice for absolutely everything. And the last problem that we checked, pizza parlour, sort of linear programming, pretty vanilla. Not natural annealer territory, but for the purpose of this benchmark, we don't mind. We don't mind. Gurobi blows all of them out of the water on this problem, because actually the linear programming problems are sort of, you can solve them algorithmically, and that is what Gurobi excels at. But the purpose here is not to be the fastest. The purpose here is to see how do these annealers cope when you start to have integer variables and code them down to binary. How do annealers deal with the Hamiltonian landscape that results? And you see that D-Wave, the D-Wave cloud service, with an interesting blip at the smallest size of size 10, so 10 different pizzas. Other than that, it performs really well up to size 100,000 and only starts to drop off a bit in quality at size 300,000 compared to a Gurobi. All the others struggle more to find an optimum solution to a linear programming problem. So MSQIO struggles from the start, drops off in quality as you increase the size, and doesn't produce feasible solutions beyond 300. Quantagonia, similar story, a bit poorer quality, but remember, early stage startup, they will improve rapidly without a shadow of a doubt. 1QBit didn't really perform all that well for us and gave up producing feasible solutions quite early. Toshiba does reasonably well, certainly handles the largest problems from any other annealer that we tested. And the D-Wave QPU, so when you just use the raw QPU rather than the cloud service, you can only tackle the smallest problem, and it just doesn't perform fantastically well on that, because you very quickly start to run into embedding problems, and linear programming isn't sort of the natural annealer territory. But it gives us an idea of the impact of what happens when you have an optimization problem involving integer numbers, and you see that you really need to give annealers quite a bit of time, more time than we've given them here in this benchmark to find the actual optimum, with the exception of the D-Wave cloud service, which performs exceptionally well. And actually, does this mean that annealers are useless for this type of problem? Well, no, not necessarily, because first of all, many business problems are actually not that simple as linear programming problems. There are complex constraints. There are perhaps even non-linear interactions, which suddenly make the problem a whole lot more complicated, and then annealers become a lot more competitive. In fact, we ran a pilot for a production optimization system for a manufacturer customer of ours, where they had Gurobi running. And taking quite a bit of time, and we basically ran that on a quantum annealer to compare results, and we found that the quantum annealer was very competitive with the classical optimizer, because the complex constraints made sort of algorithmically solving the problem much more difficult, and therefore made annealers much more competitive. And there are clever ways to use annealers in solving linear programming problems. So don't count them out, but be aware, use the right tool for the job. But clearly, you can see from this, most annealers really start to struggle within a short amount of time to find the optimum. So having integer variables that you code down to binaries, to binary variables, really makes the Hamiltonian landscape that you're trying to optimize against find the minimum of a lot tougher to negotiate for an annealer, whether that's quantum or quantum inspired. So where does that leave us? Where does that leave us as to the annealer landscape? Well, first of all, quantum and quantum inspired annealers can absolutely bring business value, and in some problems are showing clear advantage, like feature selection. So if you have an optimization problem that is complex enough that you cannot simply number crunch your way through it, and you don't have any good algorithmic shortcuts on a classical machine, but your problem is small enough to match the sort of constraints of today's quantum or quantum inspired hardware, you can actually already see real business value in using this technology. For quantum annealers, D-Wave is the big show in town. Predominantly in their hybrid offering, their Leap Cloud service that combines classical resources with their QPU, that performs exceptionally well. The QPU performs as well, and you can tune it, and you can use all sort of tricks to get it to bring value, but it has strong competition from the quantum inspired annealers out there that also perform well and don't have the connectivity problems, and therefore don't have the problems embedding the topology of your problem onto the topology of the QPU, of the quantum processor hardware. Generally though, for most business problems, you will want to use classical computing to identify sub-problems or boil down your bigger problem to a form that fits within the constraints of your quantum processor or your quantum-inspired annealer. And after D-Wave, it was Toshiba SQM Plus that definitely was the sort of the strongest offering, scaled the best, and produced the best solutions. You might have missed Fujitsu. We didn't test Fujitsu simply for commercial reasons, because their business model does not match the way sort of we work with our customers. So that's the sort of pragmatic reason why we didn't test Fujitsu. For all I have seen of it, it's a strong offering, but I can't really say very much about it. So bottom line, for optimization problems, and actually optimization problems reflect a wide range of practical business problems, from retail through manufacturing to banking, portfolio optimization, and so on. You can already see early business value in quantum computing, specifically in quantum annealing and quantum inspired annealing. So don't let anyone tell you that you are working on an abstract problem that will already only carry fruit 20 years from now. Some of the big promises, they're a number of years into the future, but there is real current and near-term value in quantum computing to be had if you pick the right problem and you pick the right technology. Thank you for your attention. My name is Peter den Haan. I will be on Discord. If you want to know more, talk to me there. Send me an email, p@haan@objectivity.co.uk, and I will be more than happy to talk to you. Thank you very much for your attention, and bye-bye.